Hey, my name is Griffin Keller. I chose the Falling Slinky lab, so this is my Physics 2211 Lab 5 Falling Slinky presentation. So for this lab, we tried to predict the motion of a falling slinky, and then we tried to analyze how the surroundings affected that slinky. As you can see on the right, this is our tracker data for the experiment. So some methods we used. In this lab, we used tracker to observe the position of the slinky in the video. We used VPython to predict the ideal motion of the slinky. And then in the lab, we attempted to see whether the slinky would stay put in the model, and we found that while it's not 100%, the bottom of the slinky mostly remains stationary. So some formulas we used Fnet equals change in momentum over change in time. We used momentum update, which is momentum initial plus Fnet times change in time. You had velocity update, which is velocity initial plus Fnet divided by mass times change in time. Then we have position update, which is position initial plus velocity average times change in time. We have the drag force formula, so drag equals negative b times the absolute value of the velocity squared in the v-hat direction. Then we have F-grav equals negative mg, and then the force of the slinky is force of tension, which equals mg. So some initial conditions for the tracker: the system is the slinky, the surroundings is the earth and the wind or any other external factors on the slinky. The mass is 0.218 kilograms, initial position negative 1.632 times 10 to the negative 3, and then it's 2.725 times 10 to the negative 4, 0. The initial height is, or the height of reference is 1.75 meters. The initial velocity is 0, 0, 0. Our time interval is 0.01. And then we initially are at 0 seconds. The first input of code goes to 5.533, and then the second one is 8.133. So this is our tracker data. They're X and Y positions versus time. We're not really looking at the X because that's really just misinputting the tracker and whatever moment. Like we don't care about the X. So for Y, you can see it goes very consistent, and then it goes down and starts moving at about 5.53 seconds. So our code conditions: the mass is 0.218. Vector, or the position and the velocity are the same. Time starts at 0. Delta t is 0.01. The gravity is 9.8. The j-hat vector is 0, 1, 0. And then our air resistance is 75. So this is the first loop. As you can see right here, we calculate the net force of the gravity, and then we calculate the net force of the tension, and we add them up to get the actual Fnet. Then we update the velocity and position using our position and velocity update formulas. We change the clock, and then we plot the curve. It's the second loop, so you see it goes to 8.13 seconds. Our net force, we have the force of gravity, and then we have the force of the drag. So we add those to get Fnet, and then we update velocity and position again, change the clock, and then plot that curve. So as our results, this is the predicted is the blue, which is our code, and then the observed is orange. So you can see it's almost identical. There's spots after about 3 seconds that it gets a little off, but it shows the exact same trend, and it really boils down to human error and just slight differences in results. So as I said earlier, the result of the lab is very accurate because the ideal and the observed motion are nearly identical. So some possible errors are some of the motion we observed from the tracker data could be due to forces that we didn't account for, so the code didn't show that. There could be some tracker misuse whenever placing the points. Could have gotten it not 100% in the middle every time, and then there could be code misinput. I could have missed something at one point. So for our discussion questions, why does the bottom of the slinky stay stationary? So the forces in the y direction cancel. Gravitational force acts in the negative y. The slinky acts in the counteracts that in the positive y. And they're equal and opposite forces, so Fnet is 0. And what if we put a large weight at the bottom? Would it stay stationary? Yes, depending on the length of the slinky and the spring constant of the slinky. If the tension force equals the gravitational force, then the weight will stay stationary until the top of the spring reaches the weight. This follows the motion of a slinky without any extra weight on it. That's the end. Thanks for watching.